Find the volume inside the hyperboloid of one sheet given by z squared equals x squared over 4 plus y squared over 4 minus 1 between the planes z equals -1 and z equals +1. So a hyperboloid of one sheet, that looks like a nuclear cooling tower. And this particular one has the z-axis running right down the middle of it. And the cross sections that are parallel to the xy plane will be circles. So this is a situation where we might want to use some kind of polar coordinates. And the way to calculate the volume inside of a surface or between surfaces, if the double integral isn't working, you could do a triple integral over the region inside of the hyperboloid in between z equals -1 and z equals +1 of just integrate 1 dv. So for x and y, we're going to use r and theta, polar coordinates. X squared plus y squared is r squared. Remember, x is r cosine theta, y is r sine theta. Everything follows from that. And dy dx is r dr d theta when you do a polar coordinate transformation. Now technically this is 3 variables. X, y, z are going to convert to r theta, and we're going to leave z alone. And when you're doing a polar coordinate transformation in 3 dimensions where you're just leaving z alone like this, it's called cylindrical coordinates. And then dy dx dz, or dx dy dz, either way, is just r dr d theta dz. The dz just stays just like the z stayed here. And you see this thing kind of looks like a cylinder, so it's nice and easy to describe in terms of r, theta, and z. Z goes from -1 to 1, theta goes all the way around, 0 to 2 pi, and r is going to vary from 0 out to this edge, and we're going to have to think about that a little bit, but that's going to work itself out very nicely, because for any particular value of z, we do have a circle as the cross section. Okay, so let's take a look. This is going to be triple integral of 1 times r dr d theta dz. Z, we'll integrate last, is going to go from -1 to 1. Theta is going to go from 0 to 2 pi. And r is going to go, looking down on this object, from 0 out to the boundary of any particular circle at a given height. And so what we'll do is we'll just take this equation and write it as z squared equals, instead of, let's first write it in the, like this. And now x squared plus y squared is r squared, so this is r squared over 4 minus 1. And that's z squared. Multiply it, solve for r. So we'll see how far r goes for a given z. We'll think of z here as being a constant between -1 and 1. So then we can add 1, z squared plus 1, and then multiply by 4, and that will give us r squared. So r is the square root of 4z squared plus 4. So r is going to go from 0 out to the edge, which will be square root of 4z squared plus 4. So we'll put that here. We'll just call this f of r, so as not to have too much up there. And now the d theta integral, we have no thetas, not in our boundary either. So integrating theta from d theta from 0 to 2 pi gives us 2 pi. And then integrating r will give us r squared over 2. And we have to go from 0 to f of r. And then we have to do the dz integral. So r squared over 2, when you plug in 0 for r, you get 0. And when you plug in f of r has this square root. So when you square it, you just get the radicand. So 4z squared plus 4 dz. Okay, so this is a pretty elementary integral here, just integrating a polynomial in one variable. And this 2, I think I forgot about that 2, didn't I? Here's r squared divided by 2, so let's just cancel this 2 out in the front. There we are. Now, so this is a straightforward integral, but let's use a little trick. This is an even function. So that means the graph of this function, if you were to have a z-axis here and an f of z-axis here, the graph of this function is actually some parabola like that. So if we're integrating, we're finding the area under it from -1 to 1. We could go from 0 to 1 and double our answer. That's a little bit nicer. So double our answer. So 2 pi, we get our 2 back. And now integrate from 0 to 1, 4z squared plus 4 dz. And that's 2 pi times, antiderivative is 4z cubed over 3 plus 4z from 0 to 1. And that gets 2 pi times, plug in 1, you get 4/3 plus 4. And when you plug in 0, you get 0. So we have 2 pi times 4 is 12/3 plus 4/3 is 16/3. And double that, that's 32/3. So 32 pi over 3. That's the volume of our nuclear cooling tower. The hyperboloid of one sheet between two planes. It has a top and a bottom.